Hi and welcome to this applied maths video. We're going to look at question 10, which is differential equations from the 2005 higher level paper. So part A asks us to solve the following differential equation. So it's x dy dx minus xy minus y equals 0. So we're going to try and separate the y's to one side and the x's to the other. Once we've done that, we're going to then integrate. So it's important that you have your log tables open in front of you on the integral calculus page. So first thing I'm going to do is I'm going to bring over the x, y, and the y. So I have x dy dx, and that is going to equal xy plus y. I'm then going to divide by x. So sorry now, that should be dy dx equals xy plus y all over x. Now I want to isolate that y. So what I'm going to do on the right hand side is I'm going to take out the y because it's common, leaving me x plus 1 all over x dy dx. Now hopefully we should be able to see how we can separate the y's and the x's. So we get 1 over y dy, bringing that y over, and we get x plus 1 over x dx. So if you're looking at page 26 of your log tables, you might think, well, that right hand side, there's nothing there to help me integrate. And you'd be correct. So what we need to do is we actually need to do a little bit more manipulation. So the left hand side is fine, dy, and what we're going to do here is we're going to separate this out. Now it has to stay in a bracket, but dividing both pieces by x, we should get 1 plus 1 over x. That means we have two distinct terms, which means integration, we just integrate each term individually, and that's very easy to integrate. So we're going to do our integration piece now. So we're going to integrate both sides. Now you can do an indefinite integral and then use substitution just to make it a little bit neater and more efficient. I'm actually going to use the values that I got as limits so I can do a definite integral on both sides. So we're going to integrate this from 1 to y. So we get the 1 from here when y equals 1. We're going to integrate the x side from 1 to x, and then we integrate. So when we integrate 1 over y from page 26, that gives us the natural log of y, and we're going to integrate that between 1 and y. And when we integrate here, the 1 integrates to x, 1 over x integrates to the natural log of x, and again we're going to do that between 1 and x. So we get the natural log of y minus the natural log of 1 is equal to x plus the natural log of x minus 1 plus the natural log of 1. Now the natural log of 1, you can double check it on your calculator, but that goes to 0. So they effectively disappear, and we're left with the natural log of y is equal to x plus the natural log of x minus 1. So remember when we were solving a differential equation, we'll go back up here to dy dx. So the top line tells us dy, so we're looking for our answer in the form y equals. So what we need to do at this point here is to do e to the power of everything. So e to the power of natural log of y equals, and same thing here, e to the power of x plus natural log of x minus 1. So this left hand side comes down to y. Now I'm going to do a little bit of cleanup here. I'm going to do e to the power of the natural log of x because there's something's going to happen there, and I'm going to leave e to the power of x minus 1. And this piece here, e to the power of natural log of x. So remember, e to the natural log, it'll just leave us with the x part. So our final answer here is y equals x e to the power of x minus 1. Now, if you didn't see that cleaning up, you would have actually got full marks at this point here. But it is nice to kind of clean it up a little bit more and it looks a little bit neater. So part B, just to mention there, part A was 20 marks, so this part B is a 30 mark question. So a mass of 9 kg is suspended at the lower end of a light vertical rope. Initially the mass is at rest. Okay, so I'm going to get my highlighter here and highlight some important bits. So 9 kg, it's at rest. The mass is pulled up vertically with an initial pull of 137.2 newtons. The pull diminishes at a rate of 1 newton per meter. Okay, so 1 newton per meter when the mass is raised. Show that the resultant upward force of the mass when it is x meters above the initial position is 49 minus x. Find the speed of the mass when it has been raised 15 meters, and find the work done by the pull on the rope when the mass has been raised by 15 meters. So there's a lot going on here. So first thing I'm going to do, I'm just going to draw a little picture. And here's my 9 kg and it's being pulled up. So the 9 kg is initially going to be given a pull of 137.2 newtons. Now, that's not the only force working on it. There is also going to be its weight due to gravity, which is 9 g newtons working down like this. So part I asks us to show that the resultant force on the mass when it is x meters above the initial position is 49 minus x. So what has happened is when it is at x meters, this is no longer true because remember, it loses 1 newton for each meter. So therefore, this new upwards force is going to be 137.2 minus x because that's how much it's lost. So it's just asked for the resultant upward force. So all we're doing here is force is equal to the upward force. So there is movement up. So remember, you're moving this way. So we're going to take this as positive, going up as positive, and down then is negative minus 9g. And when you work that through, remember gravity 9.8, it works out as 49 minus x. QED. So that part was actually a really nice simple little piece. It's not to overcomplicate it, especially in these question 10s, not to jump into trying to do integration for every part. It won't necessarily be integration at each step, so sometimes we need to set something up before we can integrate. So part B, find the speed of the mass when it is being raised 15 meters. So what we did in part I was work with the force. So just to remind you, F equals ma. That is our most basic formula. With regards integration, we have two little pieces that we usually use. So we either say acceleration is dv dt, so how quickly speed changes, or a second one we use is v dv ds, where s is our displacement. So it depends on what the question wants. So if the question is talking about time, we use the top one. If it's talking about a distance, we generally use the second one. We are talking about 15 meters here, so we're going to talk about the second one. But we're not going to call it dvds because when they talked about its movement, they said it was x meters. So we're going to work with what it says here with regards its variable, so we're going to call this x. So the force, remember we just worked out the force in the previous part, 49 minus x, is equal to mass, which is 9, times acceleration. So my acceleration is v dv dx, because you don't want to bring it in s when we already have our x. So we're going to rearrange this, and we'll work from here. So we have 49 minus x dx equals 9v dv. And we're trying to find the speed of the mass when it is being raised 15 meters. So we're going to come along and integrate it. Again, I'm going to use the definite integral here. So we're going to integrate it between 0 and 15. And we're trying to find the speed. So it has started at rest up to v. And we're trying to integrate then to get v. So let's see our integration here. So integrating this, we get 49x minus x squared over 2. And we're going to integrate that between 0 and 15. And here we get 9v squared over 2 between 0 and v. So working that through, we should get, and I'm not going to go through the full workings here, but it should be 11.76 meters per second. So you will need to square root this at the end because you'll have a v squared, and we're going to just take the positive answer here. Remember, we said that upwards was going to be our positive when we started this question in part I, so therefore we're going to take the movement upwards. So when it's been raised 15 meters, we are still moving in that upwards direction, so that will still be the positive way. Negative would just mean a change in direction. So the final thing that they've asked us to do is to find the work done by the pulley. So we would have had our formula, work is equal to force by displacement. Now, this formula unfortunately can't be used in this question, and the reason that we can't use this formula is because here of our force. And that force is not staying constant across the displacement. So we know it's going to be displaced 15 meters, but that force is not staying constant. So we need to have a different formula for work to help us in a question where that force is constantly changing. Remember, this force is diminishing every meter. It's taking 1 Newton. It's taking away 1 Newton each meter. So what we're going to do instead is we're going to take the formula, and this is a really important formula that we have already, and that's work is the change in kinetic energy. So what we're looking at instead is the difference between kinetic energy before this all starts happening and the kinetic energy when it has been raised 15 meters. So the kinetic energy, so formula for kinetic energy is a half mv squared. So my work is then a half times my mass times my v squared. I've just worked that out as 11.76. And then the kinetic energy at the start. Now there was no kinetic energy at the start because remember it was at rest. So actually what we're looking at is just subbing in to the first part there and working that through. We get 622.5. And that's measured in joules. So this particular question, because it's in a question 10, you wouldn't have been penalised for not having any of the units, but I suppose just so that we're being consistent across all the questions, I'd suggest for you to put in your units anyway. The main takeaways from this, I suppose, is to really look at that new formula for work. Make sure it's one we don't use a lot, so it's an important one to have, and don't forget your 2 different accelerations. Often students find the question 10 quite intimidating because of the word problem, but often there is very little in it. The hardest part is to try create the maths from the problem itself, but then when you get to that point, the maths is relatively simple.